Welcome to the lecture series of convolutional neural networks. In this video, we will discuss the gradient of a convolutional layer. Here is a standard convolutional network where an input would be first analyzed by a first convolutional layer, then by a second convolutional layer, third convolutional, fourth convolutional, a couple of dense layers at the end. And the question I would like to ask, how many weight parameters are there on the connections from layer 1 to layer 2. So let's look at the moment at one of these filters in layer 2. So this is a filter, and this filter would use this cone that's indicated here, which is 3 times 3 times 64. So 9 times 60 makes 540, 9 times 4 makes 36, that makes 576 parameters for one filter. But then we have 128 of these filters in that second layer, so that gives more than 70,000 parameters. And now we use gradient descent on some loss function and implement a generalized version of Backprop so as to optimize the weight parameters of all these filters. Now, I have to remind you that the convolutional layer actually has several processing stages. It has a filtering stage where we just do some linear filtering, and here are our filter parameters that I talked about. This is filter index k, which appears here. Then suppose it's a color image, so we would have our 3 color channels. Now if you go from layer 2 to layer 3, it's just a count over the channels. It might be not just 3, it might be 128 channels. And I and j are the location indices that map here to the image indices, and the image is this capital I. Then we have the nonlinearity. We take a nonlinear transform, just as rectified limit, something like rectified linear, a ReLO unit. And then we have the pooling stage. Suppose we do pooling in a 2 times 2 region, so you would take these outputs here and make them to the actual outputs, where we look in the neighborhood of +1 in both directions and pick out this maximum. Now, this is one convolutional layer. These are the 3 processing steps in one convolutional layer. And now let's see how gradient descent would go through this. So let's look at a simple example. The 2 novel aspects compared to standard deep layered neural networks is that we now have weight sharing and we will have max pooling. At the moment, I will just look at the effect of weight sharing, and let's add max pooling a little bit later. So the example is a convolutional filter, 5 times 5 times 3. I have k of these filters, and this is the filtering stage here. This is my filter index, which appears again here. Then we say it's 5 times 5 times 3, so I do the convolution over 5 in x direction, over 5 locations in y directions. I have 3 color channels or other depth channels, and the index of the color channel appears here, and the big I is the image. Then we have the nonlinearity, which could be a ReLU-like nonlinearity, and at the moment it's a single output, which is just a sum in the second layer of these ReLU activities that arrive in the second layer. Now I want to look at one specific weight of that filter. I will look at the filter with index k, and I'm just interested in this one weight, which has location indices 1, 1, and it's just looking in the color channel C equal 3. And then we use a quadratic loss function, which means we have some error function that compares the target output with the actual output of my network. And let's suppose this second layer is the output. Now, let's calculate the gradient. So let's look at dE, the derivative with respect to this specific weight. The weight is W1135, and all of this is in layer 1. And I will have my output y hat O, and then I get a minus sign and I calculate the y hat with respect to this specific weight, W1135, in the first layer. Now, the y hat is given by this equation 3 here, so let's use this. And so now I can copy this, and I get now this sum over ij and k, and I get a w I j k to this output unit, and I have my sigma prime of ai jk, and then I have the derivative aijk divided by dw with the full indices to be put here. So let's calculate this derivative. Let's look at the equation at the lower left. Ijk, I take the derivative with respect to one specific weight, the weight with index 1135. So if it's 1135, that means x has to be put to 1, I plus x minus 1, well, I plus 1 minus 1 gives just I. J plus y minus 1 plus 1 minus 1 gives just j. I want the c, I'm interested in c equal 3, so the only thing that remains is I out of this is I j 3. And I can copy the rest. A I j k, and I have here w I j k o second layer sum over I j k, and I can copy the rest. Okay, so now for this weight wi, for this derivative with respect to the weight W1135 in the first layer, I get this sum over all input locations, all images, all image locations in the third channel, in the color channel 3. So that was sort of standard, but now let's add this max pooling stage. So now let's add max pooling. If you have max pooling, then this guy here is transformed. We look in a small 2 times 2 region around ij. So if this is ij, we look at I plus 1, j plus 1, and the combination thereof and find the maximum. So let's call this x I star of ij, j star of ij. Okay, so for each ij, this is position, I look in this neighborhood plus minus 1, and I find for this position ij, I find the combination I star, j star, which is the winner in the sense it gives the maximum. So with max pooling over this 2 times 2 region, stride 1, I therefore get something very similar. So I can copy it again. Y hat some I, j, k, I, j, k, output index. I have my sigma prime and now it's no longer the index I, it's the index I star, the winner, j star, the winner for this ij, I star of ij, j star of ij, times I star, j star 3. So note that this is really shorthand notation. I mean I star of ij, j star of ij, and here the same thing. So what is this doing? For this weight, that's the derivative still with respect to the same weight, W1135 in the first layer. I sum over I and j, but I don't pick the same ij. I pick whoever was the winner. And this leads to a focusing effect of the gradient. It doesn't go through equally. It focuses on those that have been the max, that have been the winners. So it selects those indices, I star, j star, that gave the argument for that location ij. Let's look at this in a specific example. So suppose this is my input image at the bottom, and I have a filter which is an edge detector for white diagonal stripes. Now, as I apply this filter, I would get a great fit at this location and say, as I shift it continue, it continues. So these are my 5 locations, and it was in the middle that it gave the best fit. So now if I do a pooling over this region, if I pool over this region, then what it finds is this is the location I star of ij, j star of ij, which would just be the center of this region. But now let's look how the pooling would end if we have shifted. So now I do my pooling over a neighboring region, again 5 different locations, but the maximum is again the same location. And this means that the gradient focuses again on this one location where the diagonal stripe actually occurred in the roof. So if you think of this as a multiprocessing stage across a convolutional network, the gradient across the max pooling finds the location where a specific feature was found on the image. And so it can backtrack to that specific location in the feature map. So in summary, we can of course take a gradient across a max pooling layer. And what we find is during the backward path of backpropagation, the gradient automatically focuses on the location I star J star that was the winner in that small region over which the pooling was done. And now if you think of doing this over several convolutional layers, what effectively happens is that kind of the region is selected in sort of a attentional effect that is responsible for a certain output. So if the output is a house and you wiggle a little bit the output house, then that wiggling means calculating the gradient. It will point down, the gradient will point down to regions that have been responsible for this assignment house.